Okay, now let's just answer this question. Can we have more than 3 independent vectors in R3? Independent means linearly independent. Okay. So what do you think? Okay, let me just give you the example. Let's suppose in R3 you have some vectors which is something like this: 1 0 0. This is one vector. Another vector is 0 1 0. Another vector is 0 0 1. Another vector is, let's suppose, anything which is 3 5 7. Okay. Now, if I just ask you that are these 4 vectors linearly independent, then your answer probably is you will answer that no, these are not linearly independent. In fact, these are linearly dependent. Why? Because you will say that this 357 can be represented as a linear combination of these other 3 vectors, which are 1 0 0, 0 1 0 and 0 0 1, which means you will say that you can multiply this vector by 7, you can multiply this vector by 5, and you can multiply this vector by 3, and then you can get 357. So which means that 357 is linearly dependent on these 3 vectors. That's why this set is linearly dependent vectors, right? So you will say this set is basically a set of linearly dependent vectors, right? I hope you understood. Now, instead of 357, let me take some other example. Maybe let's just take some other example of your choice. Maybe let's suppose you say that it is, instead of 357, it is -2, 7, and let's suppose 23. Okay, -2, 7 and 23. So I will say that let's suppose it is -2, 7, 23. Then it is also a linear combination of these 3 vectors, right? So in fact, it is not just about this 357 or -2, 7, 23. In fact, you give me any vector in R3. Let's suppose you give me any random vector which is alpha, beta, gamma. Any random vector in R3. So let me write it alpha, beta, gamma. Then also you can say that alpha, beta, gamma can be linearly, can have a linear combination of these 3 vectors. So which means even if you write, let's suppose alpha, beta, gamma, then this alpha, beta, gamma can also be represented as a linear combination of these 3 vectors, isn't it? Let me know if you have understood this clearly or not. See, this is very simple, that if you want to represent this alpha, beta, gamma with these 3 vectors, then you can represent. It means that you put any vector here, okay? It's not just a 2, 5, 3 or maybe -2, 7, 23. It's not just about 1 or 2 vectors. You put any vector here, I will give you the coefficient, okay? And what are the coefficients? Luckily, the coefficients I do not need to calculate. It's just whatever vector you give me, the coefficients are same, right? So basically, what I'm saying here is that these 3 vectors are powerful enough to fill the space of R3, right? Which means that you give me any vector, I can represent that vector as a linear combination of these 3 vectors, right? So basically, these 3 vectors, I can say that these 3 vectors are powerful enough to fill the space of R3. Now, let me go to the next page. Okay, so let's just go to the next page and let me write it here that these 3 vectors can fill the space of R3. Now, what does this mean to say that these 3 vectors can fill the space of R3? It means that you give me any vector in R3. This statement means that you give me any vector in R3. Any vector in R3 can be represented as a linear combination of these 3 vectors, right? Can be represented as a linear combination of above 3 vectors, isn't it? So that's the power of these 3 vectors. Like, I mean, if you recall, if your elementary school mathematics, then there you used to have I cap, j cap, k cap, right? So these 3 vectors are I cap, j cap, k cap. I mean, you do not need to know this, but I'm just telling you that these 3 vectors used to be I cap, j cap, k cap, which means you have any vector, you can represent that vector as a linear combination of these 3 vectors. Let's suppose you have 2, 5, 9. Then you will just go 2 here. I mean, 2 or twice of this this vector, which is basically 1 0 0. Let's suppose this is 1 0 0. Twice of this vector is 2 0 0, and then 2 5. Let's suppose 3. Okay. Then 5 times of this and 3 times of this dimension, and then finally you will be having 2 5 3, and then you can represent this 2 5 3 as a linear combination of these 3 vectors. So these 3 vectors are very, very powerful. So again, as the same argument we did in R2. So basically these three are not the only vectors. That's the very interesting point. It is just that these are convenient vectors, that I completely agree. Why they are convenient? Because finding the coefficients is very easy, right? So it's not just like that these three are the only vector that can fill R3. In fact any three linearly independent vectors in R3 can fill the space of R3, can fill the space of R3. Okay, any three linearly independent vectors, which means, let's suppose if I say 1 2 3, let's suppose this is 1, another is, let's suppose 2 4 5, another is, let's suppose, actually I do not know whether these three are linearly independent or not. I need to check using the rank and all, but let's suppose that these are linearly independent. Okay, 3, let's suppose this is instead of 6, let me write 5 and then 7. Actually I am not 100% sure whether these three are linearly independent or not. I need to check the rank and all. Like that method we will discuss later, but for now just assume that these are linearly independent. If these are linearly independent, let's assume that these are linearly independent, then I can say these three, suppose these are linearly independent, then these three can also fill R3. So basically any three linearly independent vectors. So what do I mean by that these three can also fill R3? It means that you give me any vector. Okay, let's suppose you give me a vector which is suppose that any vector. Let's suppose this is 2 9 11. Okay, some vector. And if you ask me, can you represent this vector as a linear combination of these three vectors, which means something into 1 2 3 plus something into 2 4 5 plus something into 3 5 7, and then can you get 3 5 7, and then can you get this vector which is 2 9 11 as a linear combination of these three vectors? The answer is yes. And what are those coefficients? Actually we need to calculate those coefficients, right? So basically what I'm saying here is that you give me any three linearly independent vectors in R3. This is just random set linearly independent vectors in R3. This is random three vectors in R3. And if they're linearly independent and if they're three vectors, then any vector can be represented as a linear combination of that combination of those three vectors. Okay, you need three vectors in R3 to fill the space. Similarly, if I just give you two vectors in R3, let's suppose 1 2 3, and clearly you can see that 2 4 and then let's suppose this is 5. These two are linearly independent, right? Now if I just ask you, these two are linearly independent, if I just ask you that can they fill the space of R3? Can they fill R3? Then your answer is no, which means there are many vectors that you cannot get out of these two. Maybe let me just take one of the vector. Maybe I'm actually not sure if that is not a linear combination of these two, but suppose that one of the vector is this. Okay, 3 6 7, and it is not necessary that you always get that alpha and beta, which means that it is not necessary that every vector can be represented as a linear combination of these two vectors. Why? Because they are not filling the space. Actually, currently as per this video, I cannot tell you the proof that why you need three vectors only. I mean, why two vectors are not enough. I cannot tell you the proof for now. Just take as a statement that if you're talking about R2, then you need two linearly independent vectors to fill the space. If you're talking about R3, then we need three linear independent vectors to fill the space. And in fact, three linear independent vectors in R3 will fill the space basically. Okay, and those three linear independent vectors could be anything. Could be these three, or could be these three. It is just that these three are linear. These three are basically convenient to us. Why? Because working with the 1 and 0 is very convenient. I mean, you do not need to do much of the mathematics. But here, as a human, it is little inconvenient to work with these three vectors which are not 1 and 0. Right? That's the only difference. Otherwise, things are same. I hope you understood. So the conclusion here is that any two linearly independent vectors in R2 fill the space of R2 obviously, right? I mean, it is default. If I'm talking about R2, then it is default that I'm talking about R2 only. Similarly, I can rewrite this point and I can just say any three linearly independent vectors in R3 can fill the space of R3. So basically any 3 linear independent vectors in R3 can fill the space of R3. So this is just one point, this is another point, right? So basically you have any 3. For example, let me just give you the example. This is 1 0 0, this is just one set, but it is not the only set. 0 1 0, then 0 0 1, right? This is just one set. Maybe there are 3 other linear independent vectors, which means let's suppose this is 1 2 3, this is suppose 2 4 5, and then this is, let's suppose, 3 6 7. Actually I'm not 100% sure whether these are linearly independent or not, like I need to check the rank and all, but suppose these are linearly independent, then they will fill the space of R3. And yeah, I know that these are linearly independent. So basically there are infinitely many examples which can fill the space of R3, not just these 2 sets. There are any UVW which are linearly independent that can fill the space of R3, right? And I mean UVW which are in R3, which is having 3 dimensions, like 1 0 0, I mean these x y z 3 dimensions, and then you have those 3 vectors that can fill the space of R3. Okay, now I hope you understood this. I mean, you just take this as a statement for now. Don't try to prove it. Okay, we will prove it later. Now if you've understood this, then now can you answer this question, the original question that we started with? Okay, can we have more than 3 linear independent vectors in R3? See, let's just see that if you can answer this question by the statement that we have just seen. Suppose you have more than 3. Okay, let's suppose this is one set, and U is one vector, V is one vector, W is one vector. So suppose these are linearly independent, and now you are trying to add one more linearly independent, which is, let's suppose, Z. Can you have this whole set as linearly independent? And everything is in R3. I'm talking about R3. See, as you know that in R3, if you have 3 linearly independent set and independent vectors, then they will fill the space. So since they are filling the space, that is why Z can be obtained using UVW. That is why this whole thing cannot be linearly independent, because Z is dependent on UVW, right? Because they will fill the space. So the answer is no. So in fact, in general, you can say that can we have more than n independent vectors in Rn? Then answer is no, right? Which means in Rn, if you have, let's suppose, n vectors, let's suppose u1 or maybe v1, v2, let's suppose this is vn, these are linearly independent. Let's suppose these are linearly independent, then whatever vector you add here, that can be obtained from these vectors, because these vectors are filling the space, right? Filling the space. And why they are filling the space, that we currently don't know. So just take it as my statement that n vectors in Rn fill the space, and linearly independent vectors in Rn. Okay. Now let's just solve questions, and using the questions you will get to understand these things more clearly, right? So there are exactly n linearly independent vectors in Rn, which means you cannot have more than n basically. Okay. So I mean, the statement here is like that. I mean, there are exactly n linear independent. Oh, okay. Let me just say there are at most maybe. Okay. I mean, actually the context in which I was writing exactly might be different, but yeah, let me just say at most. So if you have more than n linear independent, I mean, if you try to add more than n linear independent vectors in Rn, that's not possible. Okay. And how to check if vectors are dependent or independent? We will come to this later. Hint, just put all the vectors in the matrix and find the rank. That we will do actually later. Okay. So this part is coming later. But for now, let me just conclude that what we have studied, right? So this is the summary or the conclusion, I can say. See, first point is that if you have two vectors, then you can easily check if they are linearly dependent or linearly independent, right? This is my first point. Actually, I mean, you can check for any set of vectors using the rank, but we will do it later. Okay. Second point is that you know that if a set containing 0 vector, then the set is linearly dependent set, right? That's the another point that you know. So these are the 2 points which you have understood. Now there are a few more points that we can add to this conclusion, or maybe I can go to the next page with the conclusion only. Now the third point is that I can say that any basically I can say that, let me just write in that way, that let's suppose 5, let me write 5, some number 5 linearly independent vectors in R5 can fill the space of R5. Now if you have 6 vectors in R5, 6 vectors in R5 can never be linearly independent, can never be linearly independent, which means if you have 5 vectors and then you try to add one more, then that one more vector must be if, see, till now let's suppose these are all linearly independent, right? And then if you add one more vector, then that vector must be dependent on all of this 5. So 6 vectors in R5 can never be linearly independent. They have to be linearly dependent only, right? You're getting my point? See, what I'm trying to say here is that if you, let's suppose you have 6 vectors and you ultimately want all of the vectors to be linearly independent, right? Just to make this claim false, that okay, 6 vectors in R5 cannot be linearly independent, let's just see. Okay, you add one vector, maybe x1, then x2, and then till now you want all of the vectors to be linearly independent, then x3, then x4, then x5. Till now you can manage, but the moment you add x6, that has to be dependent on these vectors, because these vectors are filling the space if these are linearly independent, right? I hope you understood. So that's my point. Now see, even if there are few things that are here and there you have not understood, then don't worry, let's just solve few questions, and using the questions maybe you will get to understand. Okay, so these are the few basics that I want to build. Even if you do not understand anything at all in these 2 videos or 2-3 videos, past 2-3 videos, that's perfectly fine, because we are going to revisit all of these concepts when we are going to understand the rank and all. Okay, so if you have not understood anything till now, that's perfectly fine, no problem at all. Now let's just solve few of the questions, and then this will strengthen our understanding of whatever we have studied. Okay, now first question is saying that determine if the following pair of vectors are linearly independent. See, I completely agree. Before we solve these kind of questions, I want to give a disclaimer that we have not seen any formal method of checking whether the set of vectors are linearly dependent or independent. We will see this later, but we have some guidelines. What are those guidelines? For 2 vectors I can check. If a set is containing 0 vector, then I know. Few things we know here and there. Using those guidelines, we will see if we can do those kind of questions or not. Those kind of questions will be solvable using just a little bit intuition that we have built till now. Okay, don't worry. So let's just solve. So what they're saying, can you check what they're saying? They're asking that linearly dependent or independent. Can you check whether these 2 vectors are independent or dependent? You need to multiply by -3, and then you will be getting this. So that's why you will say that these 2 vectors, right? You will say that these 2 vectors are linearly dependent. Now, can you check this? Maybe you need to multiply by -4, but then you will not be getting this. That's why this is linearly independent. Because for 2 vectors it's very easy, right? You need to multiply, I think, probably by -1. So that's why these are linearly dependent. Very easy. Now let's just solve next question. So what they are asking is that determine if the following set of vectors are linearly independent and justify your answers. Okay, so just pause this video and let me know that if you are able to find the answer or not. See, this question has been taken from Washington University, and that's a very nice question, easy question but nice question. Just let me know if you can find the answer. They want to they want to ask whether these set of vectors are linearly dependent or independent. See, this is in R3, this is in R3, this is in R3, this is in R3, right? Now can you guess? In R3 you cannot have more than 3 linearly independent vectors. That's the problem, right? So in R3 you cannot have more than 3. If there are 4 vectors, then definitely they are linearly dependent. If there are 4 vectors, then definitely linearly dependent, right? And let's suppose, I hope you understood this. Now let's suppose they ask you just about the 3 vectors. Okay, they don't give you 4 vectors, they just ask you about the 3 vectors, whether these 3 vectors they're asking are linearly dependent or independent. Suppose they ask you about these 3 vectors, right? So see, if there are 4 vectors, then you are sure these are linearly dependent. But what about the 3 vectors? Then you don't know. I mean, don't know, which means that till now we have not seen any method to check this. So for this variation, you will say that we have not studied this till now. Okay, so we have not studied how to check. Studied how to. So basically, what we can check till now is only okay. What we know till now is basically this. What we know about checking linearly dependent or linearly independent. Basically, again, just the same point that that I can write in the what I have written in the conclusion part, right? These 2 points, like I mean these 2 things, you know, if you have 2 vectors, then you can check. If there's a 0 vector, then you can do, right? So these are the few guidelines only you know till this point. So basically, what you know is basically these 2 points. If you have 0 vector, then you can immediately tell me. If you have only 2 vectors, then you can immediately tell me. Similarly, one more point, only just one more information that you have. If you have, right, if you have more than n vectors in the set, then definitely linearly dependent. Okay, vectors of form, basically vectors in Rn, which means if you have more than 3, see, if you have more than 3, then definitely linearly dependent, you know. But if it's just 3, then you don't know. Actually, we have not studied this thing. Okay, so I don't want to confuse you much. Let's just solve more questions based on just these 3 points. So whatever we are going to solve now, it will be based on just these 3 points, which means whatever we can solve, we are going to solve. Whatever we cannot solve, which means kind of questions like this, then we are not going to solve for now. Actually, it's very easy. It's not tough. It's like you just need to find the rank, and then based on the rank, you can just give me the answer. But still, like, I mean, if since we have not studied, that is why I will just say that we will just solve now few questions based on just these 3 points. Okay, because we have some guidelines, and the guidelines work only for the specific cases. Okay, for now it is working only for the specific cases. Okay, just tell me the answer of this question based on the normal intuition that we have built. So see, these are the 4 vectors, right? And which are in R3, then definitely linearly dependent. These are the 2 vectors. For 2 vectors, you can check. Okay, you can multiply 3. So the linearly dependent. For those 2 vectors, you can check. You can multiply -3, and then you can get this, but you cannot get this number, which is 9. That is why linearly independent. For 2 vectors, you can check. See, this I got using 2 vectors trick, which means if another vector is a multiple of another the first vector or not. And this I got using n+1 trick, which means like if there are more than n vectors in Rn, then they are definitely linearly dependent. If they remove just one of the vector, then I actually don't know. I'm not saying they're linearly independent or something. I don't know. Till now, I don't know. Okay. So, okay, let's not worry about what we don't know. Let's just solve few questions based on what we know. Yeah, that's one interesting question. What they're asking, if A is 3 cross 5 matrix, right? 3 cross 5 matrix means what? This is having 3 rows, 1, 2, 3 rows, and 5 columns. 1 column, second column, third column, fourth column, and fifth column. And then the columns of A are linearly dependent. So what they're saying, that A is 3 cross 5 matrix, then the columns, this column. So this column is in R3 because these are the three dots, right? Three dimension. So that's why it is in R3. Then the columns of A are linearly dependent. Now tell me, if you are having 5 vectors, see, these are the 5 vectors. Columns of A means 5 vectors. If these are the 5 vectors in R3, then definitely these are linearly dependent, right? Have you understood this? See, columns are in R3 first of all, and these are the 5 columns. Since there are 5 columns, which means they are saying that 5 vectors you have, u, v, w, x, y, something like this, and this is every vector is in R3. Since every vector is in R3, so more than 3 vectors will be linearly dependent. So that's why these are linearly dependent, and the answer is true, right? Okay, let's just solve this question, whether it is true or false. If a set contains more vectors than the entries in each vector, then if a set contains more vectors than the entries in each vector, which means that is any set v1 to vp. Okay, let's suppose it is containing p vectors v1 to vt, Vp is in Rn, which means let me just take p value as 4 and is in Rn where p is greater than n. If it is 4, then let's suppose it is 2. Okay, which means they are saying you have 4 vectors. Okay, 1 vector, second vector, third vector, 4 vectors in Rn. Rn means R2, which means you have 4 vectors in R2. Then they are saying this is definitely linearly dependent. Yeah, that is true. 4 vectors in R2, right? Definitely linearly dependent. Similarly, I mean, in general, if we are having p vectors and this is in Rn where p is greater than n, which means 4 vectors in R2, or maybe like you can say 10 vectors in R3, something like this, right? Basically, number of vectors are far more than the dimension, which means 4 vectors in R2, or maybe anything you can take here, maybe like 10 vectors in R3, something like this. If n is 3 and p is 10, then 10 vectors in R3 or something like this, then definitely it is linearly dependent. See, this question is also very nice that I have taken from Berkeley University. So I hope you understood this question. You just take the value of p and n. If you are not comfortable with p and n, you can take any value such that p is greater than n. Okay, any value such that p is greater than n, and then you can solve this question, right? Now let's just see if you can solve this question. If a set in Rn contains a 0 vector, then it is linearly dependent. Yeah, we have already seen this question. The answer is true, right? If a set is containing 0 vector, then it is linearly dependent. So basically, till now, we have just built a few basics here and there about linearly dependent and independent. Like what is linearly dependent, what is linearly independent, and based on few ideas, right? Based on these few ideas, we have solved few questions. Let's just solve one more, I think, last question. And they are asking, determine if the following vectors are linearly dependent or independent. So let's just solve this question. Just pause this video and try to solve this question. I think answer is on the next page. You can just try as an homework. Okay, just try as an homework and just see the answer on the next page that is given here. Okay, so thank you so much. I hope you understood this concept. If you have not understood, then this is completely fine. The reason being is that we are going to revisit all of these concepts in the rank. Okay, so all of this, whatever we have just studied, is actually not even the start of linear algebra. It is something that I wanted to let you know. In case if you have understood, it is fine. In case if you have not understood, then also it is fine, because now the next topic which we are going to start will basically take some help of this, but it is not ultimately necessarily that you must have understood all of this or not. Okay, I mean we will actually, this linear algebra is actually just like a process. So we will tell you the process, that okay, using this process you can solve all the questions. Don't worry, I will tell you the process, but it is better that if we build some intuition before the process. So I tried to build some intuition. We will also build some more intuition in the future videos, and then we will solve more questions. Probably by the end of this series, you will get to understand linear algebra perfectly. So if you have not understood, just have some patience and then watch more videos, like watch the coming videos. Then you will probably get to know it in the better way. I mean linear algebra in the better way. Okay. So thank you so much. Take care.